So in this section, we're talking about developing that relationship between the rate of change of a variable and the variable itself. And we'll just go through it as a good exercise here, even though we already did this in the previous video. But if we would separate the variables, we'd have dy over y equals k times dt. And we then integrate both sides, and we end up with the natural log of the absolute value of y equals k times t plus a constant, and we'll call that constant c1. And then when we exponentiate both sides according to our laws of logs, we can then solve for y, and that equals e to the kt plus the constant of integration. And using our laws of exponents, we know that that is equal to kt. We can separate up that exponent as e to the kt times e to the constant of integration. And this e to the constant of integration here is just another constant, so we'll just call that constant c. So it's really c times e to the kt is our general expression for the solution to this differential equation. And so this then comes up with our general expression for what we call growth if we're talking about positive values of k, or decay if we're talking about negative values of k. So those are the criteria to get us either growth or decay. In this example here, we take the general expression, the general exponential expression for y, and we know this is a proportional relationship between the rate of change and the variable itself. And we have these two conditions here. Here's our initial condition, and here is also another condition that satisfies the particular solution. So this is the initial. The only reason we call this the initial is because that corresponds to a time of t equals 0. And then this is just another solution that lies along that particular function. And so we need 2 points, because what we want to do is we want to come up with that particular solution, and we have 2 unknowns. So that's the whole reason for needing the second point. And so if we plug in the initial condition of 0, 4, so when t equals 0, y equals 4, we're going to go ahead and plug that in there. So we've got 4 equals to the constant e to the k times 0, and that's always nice when we can have 0 in the exponent, because that makes this whole thing e to the 0, which is 1. So we have a constant of 4, and then we can use that next condition that when t equals 5, y equals 1/2. So we can use that then to solve for our, in this case, our decay constant. This is a decay shape. It's something that decreases over time. So we have 1/2 equaling our constant, which is 4e to the k times 5. And so we have to solve for k, which means we're going to involve natural logs. So the first thing we're going to do is divide each side by 4. So we get 1/8 equals e to the 5k. And then we can take the natural log of both sides. So I'll squeeze a natural log in there. So we have the natural log of 1/8 equals 5k. And when we divide each side by 5, we get the natural log of 1/8 divided by 5. And that is our decay constant, k. And we could find a value for that. Wouldn't be a nice value, but we can go ahead and find that anyway. So if we take, get the calculator up here. There we go. Okay, so if we take the natural log of 1/8 Okay, and divide that by 5. Notice we get the negative value of 0.416. So it's negative 0.416. So that's our value for K. It doesn't matter which way we leave it. So that particular solution then is going to be 4e to the negative 0.416K. Here's a classic example of a decay function. We're talking about carbon dating here, and we're saying that carbon-14 has a half-life of 5,715 years. If we find 2 grams of carbon-14 10,000 years from now, how much was present today? So this is roughly 2 half-lives. And so if we think about it in terms of half-lives, if we've got 2 grams in 10,000 years, then if we back up, so if we kind of draw a timeline here. Okay, and so here's today, here's 10,000 years from now. And so let's just say it's 5,000. So if we back up 1 half-life, if we started out with 2 grams, that's half of what was left 5,000 years prior to it. So that's 4 grams. And that is half of what would be present today. So 8 grams, if we're talking about a half-life of 5,000 years. So here's a half-life of 5,000 years. So we should expect an answer in the 8-gram range. We're at almost 6,000 years, so we're really, to get 4 grams, we would be way out here, and then we don't have quite a half-life to go. So we wouldn't be quite at the 8-gram quantity, but we would be certainly pretty close to it. So we have this general relationship of CE to the KT. We know our K is going to be negative because it's a decay. So we have to deal with this information and this idea of half-life. And so if we kind of put this into a table, we can say, well, if we go back to the beginning when we first started recording the carbon 10,000 years ago, the beginning of that time interval, time t equals 0, let's just hypothetically say we have 100 grams. And at the end of 1 half-life then, so at 5,715 years, we should be at half that many, or 50 grams. And so this gives us our 2 data points. In order to determine the values for C and K. And the nice thing is it doesn't matter what values you use for Y, it's just that when you begin you have to have twice as much as whatever you have at the end of that half-life. So if we kind of put these numbers into this expression, we can go ahead and start with this initial condition of 100 equals CE to the K times 0. So we know we have a constant of integration of 100. And then in solving for K, we know we can set up then this situation. So this was to satisfy that situation. So now we can satisfy this condition here of 50 equaling 100 e to the k times 5715. So that's a half-life later. And so if we divide each side by 100 to solve for k, we notice we get the half back, which corresponds to the half-life. And so here's the expression for half-life for C14. And so we have to solve that for k then to find the that decay constant. And so in order to do that, we have to take the natural log of both sides. So I'll squeeze a natural log in there. So we have the natural log of a half. And that equals 5715k. And if we divide each side by 5715, we can get a value for the decay constant of negative 1.2 times 10 to the minus fourth. And so there's the constant of integration. And so we know that when we're talking about carbon-14, for carbon-14 we have this relationship of y equals CE to the minus 1.2 times 10 to the minus 4t. Now, considering the question that if we have 2 grams of C14 in 10,000 years, how much is present today? So going back to this original question here, you find 10,000 years, you find 2 grams, really specifically how much is present today, almost 2 half-lives later. We've got to come up with that initial condition. So we know that when t equals 10,000, y equals 2, and we don't know what our initial condition is, and so we're going to have to solve for that. So when we plug in 2 and solve for that initial condition, then we can go ahead and solve this. And this isn't too bad mathematically with a calculator. So e to the product of negative 1.2 times 10 to the fourth times 10,000 is going to look like a value of, there we go. So we're talking about e to the negative 1.2 times 10 to the, negative 1.2 times 10 to the negative 4. Times 10,000. Okay, so that is 0.3012, so this would be times 0.3012, and so if we divide each side by 0.3012, then we can find that initial value. So looking at that, I'm going to go ahead and take the reciprocal of that times 2, and we're looking at an initial value of 6.64 grams. So as you can see, we're kind of getting close to that initial estimate of 8 grams that was present 10,000 years prior to finding the 2 grams. An application here for exponential expressions is to model data so that we can make predictions. And in this case, they're talking about population. And so they're saying, let's use this exponential model then to come up with a particular model or a particular solution using the data from the first 10 years that they recorded population growth. So using this data here. So if this is where we began the collecting of data, then we would call this our t=0. So at time t=0, we had a population of 180, and then what we'd have to do mathematically is we'd have to say, okay, 10 years later, so at a t=10, we have this new population. So we need to have a constant, we need to find our constant, we need to find our growth value, and so it's very similar to what we've been solving in the last couple of examples. And so if we take this general growth model, this exponential model, and we go ahead and throw in the values at the beginning, we have a value when t=0, our y=180, and that's our start value. And so if we throw that in here, what we discover is that e⁻0 is 1, and so our constant out in front is our 181 value that we have at the beginning. This would be a 181 that we have at the beginning in 1960, and so really we didn't really need to go through this whole thing. That's why we can really literally just throw that initial value right into the model without any math whatsoever. We do need to find this growth rate though, and that's where that second data point is going to come in handy. 10 years later, we have a population of 205 now, and so we're going to go ahead and substitute that in a population of 205 present 10 years later. And so if we go ahead and solve this algebraically, we have 205 divided by 181 equals e⁻10k, and we're just going to take the natural log of both sides, and we're going to end up with natural log of 205 divided by 181 equals, and natural log of this is just 10k, and then we can divide each side by 10, and we end up with a growth constant of let's see, we've got 205 divided by 181, and then take that and divide that whole thing by 10. So we end up with a growth value of, not that number, because I should have put in 181, not 180. There we go, 0.01245. 0.01245. So we have 0.01245 for our growth value, and so we have a function then that is 181 e to the 0.01245 t, based on our first two data points. The next question is saying, go ahead and use your graphing calculator and put in all the data and find the model that best fits all of the data points. So here is the exponential regression on my TI-84. And so if we look at this, what we'd have to do then is we'd have to go into lists and set up some lists. So we're going to go ahead and edit these lists, and I'm going to go ahead and put in 0 And you know, we have to cut by 10, so this would be 0, 10, 20, 30, 40. So there's 10, 20, 30, and 40. And then we have to come back up here, and we started with a population of 181. And then we had 205. Then we had a population of 228. Then 250. And 282. And so there's the data in our lists, and then we can go ahead and do an analysis on that data. And so we can go ahead and go into stat and go ahead and calc. And so we can do a regression here, and it's quite obviously not a linear regression if we would graph. And we'd set up our window for to go ahead and turn on our stat plot. There we go. And then go ahead and graph and zoom stat. I think we can. There we go. Zoom stat. And so there's our values that we plugged into our lists. And so we want to then go ahead and do a regression on that. And so as we're kind of looking at the different regressions here, we have a whole bunch of different ones. There's our exponential regression. And so as we go ahead and enter, and we're just going to have lists 1 and 2, which is our default. And so here is our actual relationship we came up with. So it really is a 182, it looks like, 0.3 e to the oops, I wrote that wrong. Here's our exponential regression. It's 182.3 times 1.011 to the x. So there is our exponential model. There's our exponential model according to our graphing calculator. And it says use a graphing utility to plot the data and the graph, both models in the same viewing window, and compare the actual data with the prediction and which model better fits the data. And so if we look at this, we can go ahead then and in Y1, we can go ahead and get our statistics in there. And we're going to go ahead and I think we can grab our regression equation. There's our regression equation. And then we can also go ahead and graph this relationship here, the 181e to the 0.01245t. So if we take a look at this one first, there's our regression analysis. There's our exponential regression, pretty good fit. And then if we go back in and type in what we came up with just using the first 2 data points, that's 181 e to the 0.01245t. So there's that approximation that was just based off of those first 2 data points, remember. So if you notice, these first 2 data points kind of had a faster growth than what happened in subsequent decades. So that faster growth set us on a path that would kind of exaggerate our population over time. So not the best model, but an okay model. So this model came from our calculations, kind of overshot the population, and this one came from our stat plot on our calculator.